Hi everybody, welcome to today's Earth Science Research Group seminar. Welcome to everybody in the room and welcome to those who are joining us via Zoom and via YouTube. Today I'm pleased to say that we have Les Nagy from Scripps Institute of Oceanography, which is part of the University of California, San Diego, giving us a presentation today. So Les is from the UK originally, and he did an undergraduate degree in computer sciences at the University of Leeds. Following his undergraduate degree, he then left academia to go on to work in industry, working as a software developer for marketing companies, as well as biotech companies, and then ultimately actually then working for the European Molecular Biology Lab. Later on, after his industry experience, Les decided to come back to the dark side and come back to academia. And he went on to do a master's degree at the University of Edinburgh, which is focusing on computing optimization for GPU computations. And then he moved on to do his PhD with Professor Wynne Williams at Edinburgh, studying micromagnetism. And today, Les is going to talk about some of his work on micromagnetic modeling. Now, a little bit of background for the importance of Les's work is that in the 1940s and 1950s, a very famous scientist called Néel, he developed the first fundamental theory of magnetic recording, how essentially a magnetic particle can remember a magnetic field. And for this, he was awarded the Nobel Prize in physics. And over the last 70 years or so, this theory has been fundamental to our understanding of magnetic media. We use it in earth sciences for paleomagnetism, but it's a cornerstone of the computing industry. It's fundamental to magnetic recording that is present in almost all of our computers and technology today. Now, over the 70 years, very little has changed in this theory and how we use it, other than the recognition that actually this theory doesn't work and it's not applicable to most of the magnetic particles that we look at in nature, or actually many of the particles that we use in industry. Now, Les and his collaborators, by using fundamental physics about magnetic properties, is now completely revolutionizing this field of study. So he is now actually being able to go beyond basic Néel theory and actually develop a new understanding of fundamental recordings. And this has an amazing impact, not just on earth sciences, but across a wide range of sciences and industries. And for Les's work, he was awarded the British Geophysical Association Bulliwell Lecture. And I'm very pleased to say that earlier on this year, he was awarded a NERC Independent Research Fellowship. And thankfully, that fellowship is to come here to work with us at Liverpool. And so I'm really keen and really excited to be working with Les over the coming years. And I'm very pleased to introduce Les in his presentation here today. Thank you.
Okay, well, thank you. Thank you very much, Greg, for that really lovely introduction. And just thank you very much for inviting me to give this talk on micromagnetism. So you set me up wonderfully there, Greg. Thank you. So let's talk about some of the things, just kind of a big background picture of the importance of paleomagnetism. We know that paleomagnetism really is truly paleo. It's a technique that allows us to peer back in time and to understand what magnetic processes were happening on the Earth and even in our solar system millions and billions of years ago. But what we do know is that the recorders that we rely on, they're really complicated. So what you see here in the two pictures, A and B, is a holography image. So the holography image is a technique whereby we can directly look at what the magnetization structures are within the tiny grains that form our paleomagnetic samples. So the thing that you see there on the left, the uniform grain, in picture A, this is the single domain grain. This is the Néel domain structure that Greg was talking about previously. What we discover is that these things are actually quite rare in nature. Most of the things are complicated, they're non-uniform, and they look like the thing in the right-hand picture, in picture B. So what are some of the impacts of paleomagnetism? Well, what we do know is that it can answer questions about how the Earth's field evolved. So one of the important questions that we're interested in is we know that the Earth's field isn't a perfect dipole. And what we're really interested in is the nature of the anomalies in the Earth's magnetic field. So you see here the blue patch, which is the South Atlantic anomaly. Some of the questions that we're really interested in is, you know, are features of the field like this, are they transient? Are they primordial? How do they evolve? How do they change in time? And these are some of the questions that paleomagnetism can answer for us. Beyond the Earth, we can look at terrestrial magnetic fields. And one of the really important things here is to understand the role of paleointensities. We know that paleointensities are really difficult to recover, but micromagnetism can begin to answer some of those questions. And finally, paleomagnetism tells us something about ourselves. It tells us something about how our societies evolved. So one example here is a hut burning experiment, but it also gives us information about some very controversial findings. So there's this science paper that was fairly recently published, which proposed that a paleomagnetic event called the Matayama-Brunner's reversal was responsible for the extinction of the Neanderthals. And really questions like these rest on the paleomagnetic record. So if we don't understand what we're recording, and we don't understand how to recover those signals in our paleomagnetic samples, how do we know, how can we reconstruct these events? So basically, what are we trying to do? We're trying to understand the evolution of planetary magnetic fields, and we know that these fields are recorded in rocks, and they're particularly stored in these tiny magnetic fragments that we find within rocks. So in principle, we should just be able to go away, dig up a rock, and then measure the signal. But what we realize is that this is actually a much more complicated process, because that rock is millions of years old. It's undergone all kinds of transformations. It's been heated, reheated, it's chemically altered. And what my work is doing is it's trying to understand how all those processes affect the magnetic recorders that we essentially dig out of the ground. So I just want to give a quick outline of what the rest of the talk is going to be about. I just want to talk a little bit about rocks, domains, and micromagnetics. And then we'll look at some work that I did looking at size stability. So this is the idea of growing and shrinking a grain up to what I think is for me, very large size scale, up to the micron grain size range. And then I look at some ideas of thermal stability. So TRM and thermal signal acquisition is one of the primary ways in which rocks become magnetized and they store the Earth's ancient field. So before we begin, what are we dealing with? We're dealing with the small grains in our rocks, in our samples, and these things are the recorders. These are the things that are going to record the field. And the way that we do this is by a computational method called micromagnetics. What do we get out of a micromagnetics model? We get a structure which basically is it's a vector structure. It's a bunch of arrows. And how do we visualize that information? It's actually very complicated, and there's lots going on. And so some of the things that we really want to do is try to reduce that complexity so that we can understand what huge numbers of grains are actually doing. So in this model, what I've done here is I've plotted one micromagnetic model for a 100 nanometer grain. And what you see here is a bunch of arrows, and it's quite difficult to understand what's going on. So what we can do is we can actually calculate various quantities based on these fields. One of the things that we can calculate is a quantity called felicity. And this thing, you can kind of think of it as a measurement of local twisting. And what's really nice about this quantity is that you can really reduce the complexity of the arrows that you see on the left there to something much simpler. So a vortex structure. So what you're seeing on the left is kind of a right-handed curling structure. You can see the arrows in the main core, kind of align those with the thumb. And you can see that the arrows on the edge kind of follow the fingers of the right hand. So we call this a right-handed vortex core. But we can really simplify that down to something simple, like this tube here. And there are various other quantities that we can calculate. So there's a quantity that we define as anisotropic direction of moments, or ADM. But what that really is, it's just a measure of how far any one of the magnetization vectors in our vector field is from one of the magnetocrystalline easy axes. So in magnetite, the easy axes point along one of the cubic diagonals, and so that's the easy axis. And then the hard axes, or the things in red, point along one of the cubic edges. And by plotting these things, we can reduce the complexity that we see in our models. Additionally, what we can do is we can take our models and we can take slices through the three-dimensional domain structures, and we can simplify things down even further. And what we see when we look at this anisotropic direction of moments is we see these three spots. And we know that these three spots correspond to the vortex domain state, because as we can imagine, the vectors in the image to the right there kind of rotate through 360 degrees. And so what's happening is, because they're rotating through 360 degrees and they're pointing along one of the diagonals, we know that they must pass through each of the easy axes, and then they must pass through each of the hard axes, because they perform a 360 degree rotation. And it's features like this and simplification of the domain states that allow us to understand what's going on in our magnetic grains. So from my perspective, a rock is just a bunch of different magnetic particles, different magnetic grains. And as I said before, the arrows, the blue arrows, are going to correspond with magnetization moments that point along one of the cubic diagonals. And the red arrows correspond to magnetization moments that point along one of the cubic edges. And so when we look at our domain structures, we can start to build up a picture of the various different domain states that we see in grains. So the reason why the domain states are really important is because they are essentially causing what you measure in a magnetometer. A magnetometer is going to measure the bulk or the total assemblage of many different grains. And so the basic idea is, if we understand the behavior of those individual grains, we understand their thermal behavior, we can then begin to build back up real assemblages and real rocks. And so by categorizing all of the different domain states or magnetization states, what we find is that we see grains that have the usual uniform state. So these are the Néel grains. We see grains that vary very slightly from the uniform state, these flowering states. We see the vortex states that we've seen. And when the grains get big enough, we see very complicated domain states. They're not truly multi-domain, but they're not single vortex either. There's something in between. And so what were we really interested in? We're really interested in reconstructing planetary fields. And what we really, the way that we do it is we want to take a selection of grains that represent the kind of geometries of the materials, the magnetic materials that we see in our samples. And we know that we can't just dig things out of the ground and measure them. We have to understand the basic physics principles of how those particles are recording information. And one of the important facets of this is that we need to understand how we can reduce all that complexity that we see in our micromagnetic models. So one of the pieces of work that I've done is to look at the size evolution of magnetic grains. And you can kind of think of this as a sort of chemical remnants. A grain grows, and the question is what happens to the magnetic structure within that grain. We know that we have the single domain grain and the single vortex, but our multi-domain understanding is still limited. We can't really, we don't model up to those sizes. So this is one of the pieces of work that I did where we looked at these very, very large grains. And when we do that, we can take the individual grains, and the principle is that we take the magnetic structure for one grain, we calculate what the minimum domain structure is, we increase its size a little, and then we keep repeating this process. And by doing that, we can understand what's happening to the domain structure within the grain, or the magnetic signal. What's the effect of the grain growing on the magnetic signal? And so if we begin with something that's around 200 nanometers or 0.2 microns, we find a typical domain structure. And what I've done here is I've plotted 3 helicity isosurfaces. These really kind of pull out the domain structure and simplify it as I described before. And then the bottom 2 pictures here, you see 2 slices from 2 different angles. So one of them is some intermediate plane. That's the one on the left. And the one on the right is a plane which is perpendicular to the to a cubic diagonal. And so what we're interested in is how do these domain structures change as we increase and decrease the size of the grain. And when we do that, so here I've increased the grain size, we see that the domain structure remains a vortex structure. However, as we keep increasing the size, something is beginning to happen to the domain structure. So you can see on the grain on the very left there that these kind of edges are beginning to form, and the top right image you can see is becoming slightly more triangular. And you can also see on the bottom images here that those ellipses which correspond to the vortex core are beginning to kind of stretch out and form sort of egg-like structures. So if I keep increasing the size, what we begin to see is this kind of triangular domain structure really emerging now on the top, definitely on the top right image. And the spots there are becoming a little bit more distinct on the bottom images. And you can see kind of these blue patches. But you can see these blue patches on the image on the bottom right image are beginning to form. So if we keep increasing the size, we see that these kind of propeller type structures are beginning to form, and it's twisted. And in the bottom image, you can really see the emergence of things that look like domain states. So things that look like domains, or the types of domains that you would see in a true multi-domain grain. If we keep increasing the size, so now we're at 1.5 microns, you can really see those spokes beginning to form, looking like proper domains. that triangular structure in the middle is kind of the small, tiny spots showing that the magnetization is kind of twisting very quickly in that region, in what would be the center of the vortex core. And if we keep increasing the size further up to the maximum size that I managed to do in this simulation, you can see that we end up with these really, really well-defined domains with these really nice bright spokes, bright blue spokes that represent domain walls. And you can see that those regions, I guess you have to take my word for it, but those regions correspond to the regions in the top images, those gaps in the regions in the top images. They correspond to the domains that we see in the grain. And as we begin to decrease the size of the grain, what we find is that the structure actually remains. It's stable. And so there's hysteresis there in the structure because it's not disappearing. And now as we begin to reduce the size of the grain, we start to see that at say 1.2 micron, the domain structure that we see here is it's much more well developed and much better formed than the structure that we saw previously as we were increasing in size at 1.2. You see there, it's very fuzzy. But here, as we're going down in size, the structure really remains. You can still see those spokes. You can still see that the grain is still able to support this domain structure. As you reduce the size further, you then begin to see that much of that domain structure is beginning to disappear. It's getting washed out because the grain is now too small. It can't support that structure anymore. And if we keep reducing the size further, we end up back at our vortex structure. However, the vortex structure remains at a slightly lower, actually quite significantly lower size. So that vortex structure kind of spans a larger size going down. And what does that tell us? It tells us that there's size hysteresis there, there's size stability in the grains. But it's also telling us that these multi-domain structures form in complicated ways. So we see that the domain structure in this particular example formed as outgrowths from an inner core. And another thing that it allows us to do is it allows us to fill in the picture that we had before. So before we had this idea of what the domain, multi-domain grain would look like. But in this example, we see that here is a micromagnetic, unconstrained micromagnetic calculation of what a multi-domain grain looks like. And if we compare these numbers, with the theoretical predictions, we find that they're actually pretty good. Well, they're actually quite good. We can get the domain walls, the lengths of the domain walls seem to fit with what previous predictions give us. And we also see that the angles between the different domains are also within a very, very small amount of error. But what we also see is, of course, that the different domains are colored in blue. And that's really important because we expect, the theory tells us that in our domains, the magnetic moment vectors should point along magnetocrystalline easy axes. And if you remember, that's what blue means. It means that the grains or the moments within those regions are pointing in magnetocrystalline easy axes. So we find that our micromagnetic predictions or our micromagnetic calculations correspond really well with predictions, with previous predictions. So other mechanisms that we can look at are thermal stability of grains. And we know that thermal remnant magnetization is a really important mechanism by which grains acquire their signals. And we also know that the ambient field affects the magnetization moments in the domain structures. And so what happens is that within some ambient field, we have a grain, it's above the Curie temperature, it's going to cool in the field from above the Curie temperature, and then it's going to hit some particular temperature where that field is locked in. So how do we go about understanding that? Well, let's take a step back and go through some of the basic core principles behind thermal remnants. So we know that the Curie temperature is a temperature above which the grain just is unable to support any kind of stable magnetic state. We can think of this as a top picture there, where all the moments they're just randomly aligned because the grain is dominated by thermal noise. In superparamagnetism, there's some structure there, but the time between, or the amount of time that each of those structures, appears in the grain is very small. It's kind of flipping between coherent structures very, very quickly, too quickly to support a coherent signal. Below, which is the relaxation time, And the relaxation time is the amount of time it takes for one of these domain states to flip from one particular domain state to another. And the blocking temperature, that's a special temperature at which the relaxation time is long enough for us to say that, well, the grain now holds a coherent signal. And the final thing is that in our micromagnetic models, we're interested in LEM states. So these are the local energy minimum states. So these are the most preferred magnetic states, or the most preferred structure that minimizes a set of energies associated with that grain. And those are really important because everything that you've seen so far is an LEM state. It's a local energy minimum state. And so what we're really interested in is understanding the thermal behavior of grains. However, in the laboratory, the way that we measure these things is that we essentially take a rock and we progressively heat it to different temperatures in a given field. And we take at each temperature step, we basically replace the existing magnetization with a known magnetization. This is called a PTRM, or a partial thermal remnant magnetization. And the experiments rely on three basic laws, the Tellier laws. And these are reciprocity law. So this is the idea that at any given temperature, the amount of PTRM gained, so the amount of PTRM or TRM that we give it in our known field under experimental conditions, the amount that's gained and the amount that's lost is the same as the amount of signal lost at that temperature. The independence law, where a PTRM blocked at one temperature is independent of all of the different temperature steps that we have in our experiment. And then the additivity law. So the idea of that is basically you can take the PTRMs, you can add them up, and that gives you the total TRM. And we know that these laws are frequently violated in the laboratory. And you can really see that from the two graphs here. These are experimental, this is from experimental data. And the existing single domain theory predicts that we should have these nice straight lines where the PTRM gained and the PTRM lost is the same, and you get these nice straight lines. What we actually see when we do the measurements is we see this bowing, which we call PTRM tails. And also we see, you can see that on the graph on the left, on the right, sorry, where a grain based on single domain theory should lose, there should be a specific temperature at which the grain loses its magnetization, but of course, that's not what happens. And so what are the causes of these things? Well, one of the things that the thing that we really have to understand is, well, how do we calculate blocking temperatures? What is a blocking temperature? So as I said before, the blocking temperature is related to the relaxation time. And it's basically related to the amount of time that it takes to switch from one structure to the other. And what we can do is we can take any particular grain, seed it with a bunch of initial random guesses, and then we try to pick out all of the different domain structures that that grain can support. And then we calculate what the energy transition is between each of those grains. If we know what that energy transition is, we can just use this equation to calculate what the relaxation time is. And if we know what the relaxation times are, we can then calculate what the blocking temperatures are for each of these grains. So what you see here is a very simple grain with a vortex domain structure, and it's showing you what the energy barrier is and what the intermediate energy structures are from one LEM state to another LEM state. Then we get the delta E, that's the size of the barrier, and we just pop it into that equation, we get the relaxation time. But we did this for a whole set of grains in magnetite. These were equidimensional cuboctahedral grains of magnetite. And what we found is that the blocking temperature behavior as compared to single domain theory is very, very different. So what I've done here on this graph is I've drawn in the black line, I've drawn what single domain theory predicts. And I've really extended that way beyond the reasonable size range that single domain theory actually applies. And then in red are our thermal behavior, or our energy barrier calculations, our blocking temperature calculations based on micromagnetics. And what you see right at the beginning, when the grain is very small, it's single domain. And in micromagnetics, nothing's really single domain. So there's a slight, it comes slightly off the single domain graph, but it agrees very well with the single domain prediction. As the grain increases in size, so to about, so from 60 to 80 nanometers, we see that it begins to diverge from the single domain theory prediction. This is because the grain is flowering. And then beyond that, so from say 130, 120 nanometers, we see that the grain is really stable. It's surprisingly stable. But both of these behaviors, well, the second behavior is really surprising because single domain theory, if you were to just extrapolate the black line, obviously wouldn't hit the top of that graph. So we know that the vortex state that we see, which we think comprises the majority of the grains in our samples, those vortex states are really stable, they're super stable. However, what's really interesting is that as you transition from the single domain to the stable vortex state, you have this region in the blue box of instability. Something happens and the single domain model is completely blind to this. It just can't see the fact that there's a very sudden drop and then the stability is regained at larger sizes, but there's this small region, this very, very small window in which this happens. We don't just see that in magnetite. So what you were looking at before was magnetite. what we're looking at now is grigi. And so in grigi, for different geometries, we don't have all of the material parameters at temperature for grigi. So here we're just looking at blocking temperature. Sorry, we're looking at relaxation time versus volume versus this grain size essentially. But what we see again is this region where we have the initial graph outside the box from the small grains going up to the big grains. They're pretty well behaved. And then as they get bigger and bigger, they get more and more stable, which is exactly what we expect. And then we hit that blue box, and they're again very unstable before picking up again. So it's obvious that this effect is geometry dependent, but we do see it in different materials because we also see this in iron. In iron, it's very, very difficult to see because it happens extremely quickly. As you see in that small blue box there, there's a very sharp uptick and then a drop. But you can see this much better in what we call the Pulaia diagram or the Pulaia nomograms, where we look at what the relaxation time is for a particular set of temperature. So we look at what the relaxation time is versus temperature for a set of grains of different sizes. And when we do that, we see that, again, we have nice, we have a line with a very nice sharp gradient, which corresponds to a fairly stable grain. And then we pass through the this energy, this region of instability, where we see in the nomogram the grain becomes the gradient of the temperature versus relaxation time becomes much shallower, and this indicates that the grain is much less stable before again it gets bigger again, and then it recovers, it gets much more stable. So we see this effect in lots of different materials, and for different geometries. It's clearly geometry dependent. And so some of the work that I've been doing at the moment is trying to understand exactly how the geometry affects the relaxation time. What is the effect of the geometry in our grains? And as you can imagine, this is a hugely computationally expensive process. At the moment, we've got, I've got there 1.8 million models. We've got way in excess of that. And one of the things that we're trying to do is process all of these models and to actually come up with what the thermal behavior is for all of these different grains. But even without that, what we see is some really surprising results. So what you're seeing here is a grain which is being elongated. So we're looking at the local energy minimum. These are the most magnetically stable domain structures for a grain that's been elongated. And as you can see, from the beginning, we get something that's pointing along the diagonal. And then when we get to about 30% elongation, something very surprising happens. In single domain theory, we would expect the net remnants or the net magnetization to point along the axis of elongation. This is not what's happening in these grains. Watch as it increases there. The grain is, the net remnants is perpendicular to the axis of elongation. And so that's its most energetically favorable state. And that has big consequences on paleomagnetic interpretations. And so really, I just said that I'm working on this very large database of domain structures. And one of the things that I'm trying to do is build this virtual paleomagnetic laboratory. And the idea is that we've got a good handle on what's happening micromagnetically, thermally for individual grains. But now, can we use machine learning and big data to begin to take all of this all of these small simulations and put them back together and to form real rocks and to simulate real rocks and to actually understand what's happening in our paleomagnetic samples. So thank you very much for listening.
Thank you very much, Les, for a really exciting presentation there. So we'll have time for about 10 or 15 minutes worth of questions, either in person or on Zoom or YouTube. If you have any questions for from YouTube or Zoom, please just type them into the chats, and one of our people here will read it out for you. But I'll open the floor to questions here.
Lovely talk. I really enjoyed it. So coming from a practical paleomag perspective, then, you know, the crucial thing here is the net remnants, what comes out, right? The flux leakage. And, you know, my limited understanding suggests that it's quite a positive message, really, because you've got these larger vortex grains that are the most stable,
yes,
with the longest relaxation times, and they're also going to be, you know, correspondingly, have a higher amount of magnetization, be more dominant because they're just bigger. Is that oversimplified?
Yes. Yeah, that's the very broad big picture. Is that what we see with the vortex grains, or with the vortex state grains, is they're bigger, they have more magnetization. Admittedly, you have to be a little bit careful because the magnetization is constrained to the vortex core. However, they're super stable. They're the bigger ones are really stable, and you're quite right. They constitute a huge part of the paleomagnetic measurement that you're gonna see in a laboratory. Yeah.
Great. So it's a linked question then. This zone of instability that you found, that's like a you know, not such a great finding for us.
Yeah.
Do you think that's likely to be a practical problem?
The thing about the zone of instability is that there's much toing and froing about this. The thing about that zone is that they are by nature unstable. And so in a thermal experiment, you should in principle see an effect similar to superparamagnetism. You should be able to wipe them out. What's a lot more interesting is in the elongate grains, you're going to see different domain states, and the energy transitions between those domain states are not going to be symmetrical. They're going to be asymmetric. And what's maybe I can an extra slide. So I have this extra slide. This is a grain that's 30% elongate. And what's really interesting about this is that you're seeing in red and blue, you're seeing something where so this is a 30% elongate grain. It can support two basic types of domain structure, one of which is one of these perpendicular things that I was talking about, and then one that's parallel along the axis of elongation, right? But the energy barriers are asymmetric. And so what you're going to see in this thing is some really complicated thermal behavior. And so the speculation is, as you drive up and down, as you heat this, and as you go up and down, what you're looking at, the axes are handily, they're not labeled, but what you're seeing along the bottom is temperature, and what you're seeing on the side is logarithm of relaxation time. And then this little grey dotted line, this is lab time, so that's supposed to correspond to about 100 seconds or so. And what you see is there's some really complicated stuff going on at a fairly low temperature, around 150, and then there's another blocking temperature, which is happening at around 500, right? Some really complicated behavior happening there. Is something like this going to be the cause of a tail?
Do we have any other questions from the audience here, or do you have anything online?
Oh, actually, John Wheeler has a question. So I think the problem is, John, I'm not sure that we're going to be able to hear you. So if you could type it, then we can read it out on your behalf. And whilst he's typing, I will ask my question, which is, so as a volcanologist who's working on igneous intrusions, my main experience with magnetism is through the magnetic susceptibility and AMS. Yeah. And so I just wondered whether your work is sort of how that's kind of linking in with those kind of signals, and because basically we would use those as records of flow in magma, and so I was interested about the connection there.
Yes, so we can definitely model. We can model coercivity. We can measure. We can model various room temperature measurements that you would take, magnetic measurements. So you could, in principle, you can model AMS. And so one of the things that we have been looking at is modeling, well, not AMS, but looking at coercivities. And looking at the coercivity spectrum and trying to connect that to the thermal spectrum. So that's some of the work that we've been doing. You can look at things like fabrics and anisotropy. Absolutely, yeah. You can anything room temperature, magnetic observations. You can model using micromagnetic models, and in fact we do that. We look at coercivities, we look at forks. AMS is it's a bit more to it, but in principle you can absolutely model those things.
It's really interesting, thank you. So we have a question from Zoom, which is from John Wheeler. And he says, you haven't shown the equations behind the model, no. but since big grains behave differently to small grains, there must be a length scale built into the physics and equations somewhere. Is that right? And is there a simple verbal summary of what that length scale is?
A length scale built into the model. Yes. And that happens at the exchange interaction. That happens with the exchange interaction. So the exchange interaction is a local effect, and it's essentially something that wants neighboring moments to align with each other. The exchange interaction has a distance, and it's responsible for some of these complicated local variations in the field, because you've got essentially micromagnetism. There are, well, let's say there are three field components, just to simplify. There's a demagnetizing field, and that kind of wants to form these closure domains. It wants to, all of the fields are in opposition to each other. There's a magnetocrystalline anisotropy, which is the thing that you saw in one of those images there. It wants the moments to point along one of the diagonal directions, and then there's the exchange interaction, and that wants the moments to lie parallel to each other, and that's kind of where the length scale comes in. It's the length scale over which the exchange interaction operates. Essentially, the demagnetizing field is global. It affects everything. The magnetocrystalline anisotropy is really local, because it's just based on the direction, and then in the middle is the exchange interaction. What's the length scale of it? Is it some? I can't remember. I don't know what the length scale. It's whatever the domain wall width is, but I can't remember what it is. But that's kind of the length scale over which it's acting. Does that answer the question? Does that?
I believe so. Thank you.
Okay.
Do you have any other questions from the audience live? If not, I have but I think will be a quick one. So essentially, when you've talked about the kind of applications for basically paleomagnetism and earth sciences, the kind of things that you're doing, what other kind of potential applications do you think that they would have outside of earth sciences?
Okay, I mean, you can look at you can model the magnetosomes in in biogenic magnetite. So for the audience may not be aware that there is an organism called a magnetized bacteria, and in that organism there's a little organelle called a magnetosome, and the bacteria uses this magnetosome essentially to optimize the strategy by which it finds resources in whatever environment it's in. We can use, because the magnetosome consists of chains of geometrically very well defined chains of magnetite, we can understand the biogenic processes for those grains. For environmental magnetism, we know that in artificially produced processes, they also produce magnetite, and those magnetites, they have very different geometries to the geometries that we see in naturally formed magnetites. And so there's a possibility there of using micromagnetic modeling to understand, well, what are the differences of those geometries? Can we distinguish between artificial sources of magnetite, which may be linked to sources of environmental pollution, or natural sources of magnetite? So there's lots of different applications. The recording industry, I mean, the recording industry is entirely built on top of understanding micromagnetics, and there's things like magnetic cooling. You can use micromagnetics to understand the magnetic cooling effect, to kind of build refrigerators essentially, which run on magnetism. So there's loads of different things.
Thank you very much, Les. Unless we have any other questions, I would just like to ask everybody to give Les another round of applause for an excellent presentation. Thank you very much, and thank you all for joining us today for the